Hello friends, welcome to this video about the restoring binary division process. The objective of this video is to explain the binary division method called the restoring division. This new method has been generated as a result of the engineering efforts to simplify the circuit hardware for the binary division. In the previous video, we explained the general approach on how to perform the division with binary numbers. It is called the basic binary division process and constitutes a basis to understand the improved process presented in the next videos. If you haven't seen it, I recommend you to check it first. What are the differences between this new restoring method compared with the previous basic binary division? In the basic method, which practically follows the traditional paper and pencil approach, we are successively shifting the divisor to the right, subtracting the divisor from the successive partial reminders, and the partial reminders are maintained aligned in a fixed position. But in this new restoring division method, we are doing it in the other way around. That means we are shifting the partial reminders to the left, while the divisor is kept in a fixed position. So, mainly, instead of shifting the divisor to the right, we maintain it in a fixed position and we shift the partial reminders to the left. The advantage of this small strategies change, as we will see, is to help simplify the division circuit implementation hardware. Let's see that with an example. Here I take the same example as in the previous video. This is the basic binary division paper and pencil method, already explained in detail in the previous video. And this is the new method. Let's remind first the process of the basic binary division method. This is the dividend and this is the divisor. First, we are comparing the first three digits of the dividend with the divisor 110 to see if it goes or not. Because the divisor is bigger than the first three digits, in this case we need to write 0 in the quotient. Now we need to try with the first four digits. So we compare again, and in this case the divisor goes because it is smaller. So we write 1 in the quotient and we make the subtraction. Now we bring down the next bit of the dividend and we compare again to see if it goes or not. In this case it goes. So we write another 1 in the quotient and we make the subtraction. And so on, we continue the process comparing and performing the subtractions. At the end, after all iterations, once we have covered all the bits of the dividend, we get our final quotient and the remainder. Now let's see the new method called the restoring division. First, we are comparing the first three digits of the dividend with the divisor 110 to see if it goes or not. Because the divisor is bigger than the first three digits, In this case, we need to write 0 in the quotient. Now we shift the remainder to the left, we keep the divisor in the same place, and we try with the first 4 digits. So we compare again, and in this case the divisor goes because it is smaller. So we write 1 in the quotient and we make the subtraction. Now again we shift the remainder to the left and we keep the divisor in the same place, and we try with the first digits. We compare again to see if it goes or not. In this case it goes, so we write another 1 in the quotient. And so on, we continue the process, shifting the remainders to the left and keeping the divisor fixed in the same position, comparing and performing the subtractions. At the end, after all iterations, once we have covered all the bits of the dividend, we get our final quotient and the remainder. So, as you see, using both methods, the quotient we obtain is the same, and the remainder is the same. So, the result we get is correct. Note that in the old method, we shift right the divisor, while in the new method, we keep always the divisor in the same position. Note also that in the new method, the partial remainders are shifted to the left. The blue straight arrow means shift left. The blue round arrow means it doesn't go, so try again, restore. As seen in the previous video, in the basic method, the partial remainders were calculated on the basis of this division equation and this partial remainder equation, where D is the dividend, Q is the quotient, W is the divisor, and R is the remainder. But now in the restoring method, the division equation is the same, but the remainder equation is different. What in fact we are applying is this equation instead of this equation, which means we are multiplying the remainder by 2 and then we are subtracting the divisor, because Q is always 0 or 1. As you know, multiplying the remainder by 2 means shifting the partial remainder to the left. So this is the arithmetic reason that supports the new restoring method. One thing we have seen from this example is that at every step we are checking where the divisor goes. That means whether we can subtract the divisor or not. But the question is, in an actual computer hardware circuit, how we can check that? How we can check whether it goes or does not go? The answer is We can do it by making a trial subtraction. That means, let us do a subtraction and see if the result is becoming negative or not. If the result of a subtraction is becoming negative, then you can say that it does not go. If the result remains positive, then it is fine and we can proceed. In binary sign numbers, we know that the sign bit of a number is the first bit. If the sign bit is 0, the number is positive, and if the sign bit is 1, the number is negative. So, for the hardware, this is a good practical solution. Because for the hardware, it is easy to detect if a number is positive or negative just by checking if the first bit of the result is 0 or if it is 1. If it is 0, the number is positive. If it is 1, it is negative. So this is the property that it is used. If after a subtraction the sign bit is negative, it means the divisor it does not go. The only problem is that in this case, as we have already made the subtraction, we will have to add the divisor back again to restore the situation. That is, we have to restore the original value before going on with the process. So, in this case, a restoring step may be required. This is why this methodology is called the restoring division. So, the concept of what we are doing is this. We make a trial subtraction, and then you can add it back by means of a restoring step when we see that it does not go. This process is shown in the following flow diagram. This is the flow diagram of the restoring division process. This is the shift left of the partial remainder. And this is the trial subtraction step. If the result is positive, means it goes, so the quotient digit is 1. If the result is negative, means it does not go, so the quotient digit is 0, and we need to add back the divisor to restore the partial remainder. This is called the restoring step. This is the counter, and this is the iteration loop. Once all the bits of the dividend have been covered, we get our final quotient and the remainder, and we stop. So, this is the basic restoring division algorithm. This is how the computer solves the tricky story to find out if it goes or if it does not go. We as people, we are able to do so through a try and error method, but the machine cannot do that. So, they do a trial subtraction, and depending on the result, they need to step back. In summary, the restoring division method has been generated as a result of the engineering efforts to simplify the circuit hardware for the binary division. In the basic method paper and pencil, we are shifting the divisor to the right and keep in a fixed position the successive partial remainders. But in this new restoring division method, we are doing it the other way round. That means we are shifting the partial remainders to the left while the divisor is kept aligned in a fixed position. The way the restoring method handles the tricky story of finding out if the divisor goes or if it doesn't go is by making a trial subtraction and a restoring a step. That's why this methodology is called the restoring division. In the present video, the fundamentals of the restoring strategy and the flow diagram of the restoring division have been presented and explained. That's all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. Thank you. In the next video, we will explain how to implement the restore binary division circuit.